James Hopwood JeansThe Mathematical Theory of Electricity and Magnetism. All books on my channel are in public domain. Subsequent sections of the books are organized in playlists. Links provided in the last minute of the recording. Please subscribe, like and comment. Please be mindful that this book was printed in 1907. Some conceptions and units might be different from what is considered a standard today. Mathematical expressions of the law of the inverse square. 1. Values of potential and intensity. 38. We now discuss the values of the potential and components of electric intensity when the space between the conductors is air, so that the electric forces are determined by Coulomb's law. If we have a single point charge E1 at a point P, the value of R, the resultant intensity at any point O, is E over PO squared, and its direction is that of PO. Hence, if theta is the angle between OP and O prime, the line joining O to an adjacent point O prime, the work done in moving a charge epsilon from O to O prime equals epsilon R cosine theta dot O prime equals epsilon R brackets OP minus O prime P equals minus epsilon R dr, where OP equals R, O prime P equals R plus dr. Hence the work done against the repulsion of the charge E1 in bringing epsilon from infinity to O prime by any path is minus epsilon integrated between R to infinity and R equals O prime P of R dr equals minus epsilon integrated between R to infinity and R equals O prime P of E1 over R squared dr equals epsilon E1 over R1, where R1 equals O prime P. If there are other charges E2, E3, the work done against all the repulsions in bringing a charge epsilon to O prime will be the sum of terms such as the above, say epsilon times brackets E1 over R1, plus E2 over R2, and so on, where R2, R3, are the distances from O prime to E2, E3, so that by definition, V equals E1 over R1, plus E2 over R2 and so on. 39. It is now clear that the potential at any point depends only on the coordinates of the point, so that the work done in bringing a small charge from infinity to a point P is always the same. No matter what path we choose, the result assumed in paragraph 33. It follows that we cannot alter the amount of energy in the field by moving charges about in such a way that the final state of the field is the same as the original state. In other words, the conservation of energy is true of the electrostatic field. 40. Analytically, let us suppose that the charge E1 is at x1, y1, z1, E2 at x2, y2, and z2 and so on. The repulsion on a small charge epsilon at x, y, z resulting from the presence of E1 at x1, y1, z1 is E1, epsilon over brackets x minus x1 squared plus y minus y1 squared plus z minus z1 squared, and the direction cosines of the direction in which this force acts on the charge epsilon. R. Equation on the screen here. Hence the component, parallel to the axis of x is E1, epsilon brackets, x minus x1, divided by square brackets x minus x1 squared plus y minus y1 squared plus z minus z1 squared end of square brackets all to the 3/2 power. By adding all such components, we obtain as the component of the electric intensity at x, y, z. X equals sigma E1 brackets x minus x1 divided by square brackets x minus x1 squared, plus y minus y1 squared plus z minus z1 squared, end of square brackets, all to the 3/2 power. This is equation 11, and there are similar equations for y and z. We have as the value of V at x, y, z by equation 6, here a set of equations on the screen, giving the same result as equation 10. 41. If the electric distribution is not James Hopwood JeansThe 41. If the electric distribution is not confined to points, we can imagine it divided into small elements which may be treated as point charges. For instance, if the electricity is spread throughout a volume, let the charge on any element of volume dx prime dy prime dz prime be ρ times dx prime dy prime dz prime, so that ρ may be spoken of as the density of electricity at x prime, y prime and z prime. Then in Formula 11 we can replace E1 by ρ dx prime dy prime dz prime, and x1, y1, and z1, by x prime, y prime and z prime. Instead of summing the charges E1, we of course integrate ρ times dx prime, dy prime, dz prime, all those parts of the space which contain electrical charges. In this way we obtain two equations here, on the screen. These equations are one form of mathematical expression of the law of the inverse square of the distance. An attempt to perform the integration, in even a few simple cases, will speedily convince the student that the form is not one which lends itself to rapid progress. A second form of mathematical expression of the law of the inverse square is supplied by a theorem of Gauss which we shall now prove. And it is this expression of the law which will form the basis of our development of electrostatical theory. Gauss theorem. 42. Theorem. If any closed surface is taken in the electric field, and if n denotes the component of the electric intensity at any point of this surface in the direction of the outward normal, then surface integral n ds equals 4 pi times E, where the integration extends over the whole of the surface, and E is the total charge enclosed by the surface. Let us suppose the charges in the field, both inside and outside the closed surface, to be E1 at P1, E2 at P2 and so on. The intensity at any point is the resultant of the intensities due to the charges separately, so that at any point of the surface, we may write n equals n1 plus n2 plus and so on, where n1, n2 are the normal components of intensity due to E1, E2. Separately, instead of attempting to calculate surface integral of n ds directly, we shall calculate separately the values of surface integral of n1 ds, surface integral of n2 ds. The value of surface integral n ds will, by equation 12, be the sum of these integrals. Let us take any small element ds of the closed surface in the neighborhood of a point Q on the surface and join each point of its boundary to the point P1. Let the small cone so formed cut off an element of area d sigma from a sphere drawn through Q with P1 as center, and an element of area d omega from a sphere of unit radius drawn about P1 as center. Let the normal to the closed surface at Q in the direction away from P1 make an angle theta with P1, Q. The intensity at Q due to the charge E1 at P1 is E1 over P1Q squared in the direction PQ, so that the component of the intensity along the normal to the surface in the direction away from P1 is E1 over P1Q squared cosine of theta. Instead of attempting to calculate surface integral of n ds directly, we shall calculate separately the values of surface integral of n1 ds, surface integral of n2 ds. The value of surface integral n ds will, by equation 12, be the sum of these integrals. Let us take any small element ds of the closed surface in the neighborhood of a point Q on the surface and join each point of its boundary to the point P1. Let the small cone so formed cut off an element of area d sigma from a sphere drawn through Q with P1 as center, and an element of area d omega from a sphere of unit radius drawn about P1 as center. Let the normal to the closed surface at Q in the direction away from P1 make an angle theta with P1, Q. The intensity at Q due to the charge E1 at P1 is E1 over P1Q squared in the direction PQ, so that the component of the intensity along the normal to the surface in the direction away from P1 is E1 over P1Q squared cosine of theta. The contribution to the surface integral n1 ds from the element of surface is accordingly plus or minus E1 P1, Q squared cosine of theta of ds. The plus or minus sign being taken according as the normal at Q in the direction away from P1 is the outward or inward normal to the surface. Now cosine theta ds is equal to d sigma, the projection of ds on the sphere through Q having P1 as center, for the two normals to ds and d sigma are inclined at an angle theta. Also d sigma equals P1Q squared d omega. 4. D sigma, d omega are the areas cut off by the same cone on spheres of radii P1, Q and unity respectively. Hence, E1 over P1Q squared cosine of theta, ds, equals E1 times d sigma over P1 times Q squared equals E1 d omega. If P1 is inside the closed surface, a line from P1 to any point on the unit sphere surrounding P1 may either cut the closed surface only once as at Q in figure 8, in which case the normal to the surface at Q in the direction away from P1 is the outward normal to the surface, or it may cut 3 times, as at Q prime, Q prime prime, Q triple prime, in which case 2 of the normals away from P1 are outward normals to the surface, while the third normal away from P1 that at Q prime prime in the figure is an inward normal, or it may cut 5, 7, or any odd number of times. Thus a cone through a small element of area d sigma on a unit sphere about P1 may cut the closed surface any odd number of times. However many times it cuts, the first small area cut off will contribute E1 d sigma to surface integral N1, ds. The second and third small areas, if they occur, will contribute minus E1 d sigma and plus E1 d sigma respectively. The fourth and fifth, if they occur, will contribute minus E1 d sigma and plus E1 d sigma respectively, and so on. The total contribution from the cones surrounding d sigma is, in every case, plus E1 d sigma. Summing over all cones which can be drawn in this way through P1, we obtain the whole value of surface integral N1 ds, which is thus seen to be simply E1 multiplied by the total surface area of the unit sphere round P1 and therefore 4 pi E1. On the other hand, if P1 is outside the closed surface, as in figure 9, the cone through any element of area d sigma on the unit sphere may either not cut the closed surface at all, or may cut twice, or 4, 6, or any even number of times, if the cone through d sigma intersects the surface at all. The first pair of elements of surface which are cut off by the cone contribute minus E1 d sigma and plus E1 d sigma respectively to surface N1 ds. The second pair, if they occur, make a similar contribution, and so on. In every case, the total contribution from any small cone through P1 is nil. By summing over all such cones, we shall include the contributions from all parts of the closed surface, so that if P1 is outside the surface, surface integral N1 ds is equal to 0. We have now seen that surface integral N1 ds is equal to 4 pi E1 when the charge E1 is inside the closed surface, and is equal to 0 when the charge E1 is outside the closed surface. Hence surface integral N ds equals surface integral N1 ds plus surface integral N2 ds and so on, equals 4 pi times the sum of all the charges inside the surface equals 4 pi times E, which proves the theorem. Obviously, the theorem is true also when there is a continuous distribution of electricity in addition to a number of point charges. For clearly we can divide up the continuous distribution into a number of small elements and treat each as a point charge. Since n, the normal component of intensity, is equal by paragraph 36 to minus partial of v in respect of n. Where partial in respect of n denotes differentiation along the outward normal, it appears that we can also express Gauss' theorem in the form surface integral partial integral v in respect of n of ds equals minus 4 pi time e. Gauss' theorem forms the most convenient method at our disposal of expressing the law of the inverse square. We can obtain a preliminary conception of the physical meaning underlying the theorem by noticing that if the surface contains no charge at all, the theorem expresses that the average normal intensity is nil. If there is a negative charge inside the surface, the theorem shows that the average normal intensity is negative, so that a positively charged particle placed at a point on the imaginary surface will be likely to experience an attraction to the interior of the surface rather than a repulsion away from it, and vice versa if the surface contains a positive charge. Corollaries to Gauss' theorem. 43. Theorem. If a closed surface be drawn, such that every point on it is occupied by conducting material, the total charge inside it is nil. We have seen that at any point occupied by conducting material, the electric intensity must vanish. Hence at every point of the closed surface, n equals 0, so that surface integral n ds equals 0, and therefore, by Gauss' theorem, the total charge inside the closed surface must vanish. The two following special cases of this theorem are of the greatest importance. 44. Theorem. There is no charge at any point which is occupied by conducting material, unless this point is on the surface of a conductor. For if the point is not on the surface, it will be possible to surround the point by a small sphere, such that every point of this sphere is inside the conductor. By the preceding theorem, the charge inside this sphere is nil, hence there is no charge at the point in question. This theorem is often stated by saying, the charge of a conductor resides on its surface. 45. Theorem. If we have a hollow closed conductor, and place any number of charged bodies inside it, the charge on its inner surface will be equal in magnitude but opposite in sign to the total charge on the bodies inside. For we can draw a closed surface entirely inside the material of the conductor, and by the theorem of paragraph 43, the whole charge inside this surface must be nil. This whole charge is, however, the sum of 1, the charge on the inner surface of the conductor, and 2, the charges on the bodies inside the conductor. Hence these two must be equal and opposite. This result explains the property of the electroscope which led us to the conception of a definite quantity of electricity. The vessel placed on the plate of the electroscope formed a hollow closed conductor. The charge on the inner surface of this conductor, we now see, must be equal and opposite to the total charge inside, and since the total charge on this conductor is nil, the charge on its outer surface must be equal and opposite to that on the inner surface, and therefore exactly equal to the sum of the charges placed inside, independently of the position of these charges.